Here we go, showtime. Good afternoon, everyone, and welcome to today's webinar on transformer protection. My name is Eduardo Iglesias, and I'm currently the Senior Regional Manager for the industrial sector in the Southeast U.S. And on behalf of the GE Grid Automation business, I would like to thank you for taking the time to participate in this session, which, by the way, is part of a biweekly webinar series that, together with my colleague, Tim Fahey, and supported by the team of application engineers led by Terry Smith, is planned to continue until the end of the year. So be on the lookout early next week for the following one, which is probably going to take place on Thursday, August 13th. Now, before we get started with today's technical content, I would like to mention a couple of housekeeping items. First and foremost, and as a general disclosure comment, please be advised that this meeting is being recorded. The recorded video will be available for on-demand viewing later on tomorrow, and if not on Monday at the latest, I will send all the participants an email with a copy of the presentation and the link for you to view this recording for the next 60 days or so, which is the time that the Teams platform allows to have this available for on-demand viewing. If you need your certificate of completion, please make sure to email Tim and I later so we can get this out to you. Unfortunately, the platform that we're using does not spit out the certificates automatically. So make sure to email us with your information so we can get that certificate out to you within the next few days. Okay. If this is your first time participating in the Teams live event, please understand that we cannot hear you. Everybody's muted. The way that we will take questions is there's a chat box on the top right-hand corner that has like a question mark. Please submit all your questions there. Do not wait for the presentation to be over to do this. Alongside the presenter, we have other application engineers on the lines that will be answering your questions as they come in. Some of them we may want to wait for the end, but please submit all your questions as they come. Okay. With that said, I think that I would like to introduce our today's speaker, which will be Terry Smith. He is our leader for the technical application engineers in the North American region. So Terry, the floor is all yours.
All right, thank you, Eduardo, and thank you all you guys out in the interwebs that are listening and watching the presentation today. Thank you for joining me. So today I'm going to talk about transformer protection. I'm going to talk a little bit about the fundamentals of transformer protection, you know, how we do it and what we do and why we should do it, those sort of things. And then we're going to spend some time actually setting up some transformer protection relays. So hopefully at the end of the session, we'll go through a application example where we take a particular transformer and then set it up. Okay, so let's talk about some of these transformer fundamentals. So this is a video that I'm sure a lot of you guys have seen. This particular video shows a transformer, you know, an arcing in a substation. It doesn't get cleared, and eventually it ruptures the tank. The bad thing about a transformer is not only is it an expensive device, it's a device that's full of mineral oil, and that's the mineral oil is the dielectric. I'm going to turn that off because I don't like talking over that arcing in the fire. But nonetheless, the mineral oil is a combustible material, right? So it has about the same combustible properties as diesel fuel. Now, you No, diesel fuel doesn't burn particularly well, but once it gets hot, it off-gases other hydrocarbons that burn really well. And that's what happened in this instance. So for that reason, transformer protection is very important. It's very important we do it correctly and not do something like happened in this instance with this transformer fire in this video that I just showed. I think this is the first time I've tried to share a video on a Teams event. I hope that went through. If it didn't, trust me, it was spectacular. Or you can just look it up on YouTube and watch. Okay, so let's talk about some of the protection functions that we might want to have on a transformer. Now, transformers come in a lot of different varieties for different reasons, right? So they might be generator step-up transformers. They might be utility inter-tie transformers to an industrial facility where we're stepping the voltage down to the industrial facility, or distribution transformers where we're doing the same thing. Might be an auto transformer where in a utility high voltage switch yard. But the type of protection that we'll employ on a lot of these transformers will depend on where we find it at. Now, the transformers we're going to deal with today are mainly around the transformers that we'll find in the industrial world. But most of these principles also apply to the utility world, whether that's the distribution world or the transmission world. Now, as we look at this particular transformer here, we've got several protective elements that we're going to employ. Now, the best and fastest protection, the one that we always want to have on these really expensive transformers, is the transformer differential here, the 87T. Now, the 87T is meant to provide a zone of protection from this CT to this CT. So if we look at the 87T, it's going to trip for phase faults here and maybe some ground faults, depending on the fault current level. So it should trip for faults inside of that red zone there. Now, we're probably also going to need a 51 element, right? A 51 element here, because if we have a source up here, right? So if we got a source somewhere up in the top up here, and we've got a fault down here, that through fault, that differential, that is outside of the differential zone of protection. Differential's never going to operate for that. So that's going to be a problem for us because we may overload that transformer with that through fault. So that's where that differential comes in. Excuse me, I'm sorry. Time overcurrent comes in, the 50-51 here. We're probably also going to need some protection for the fact that we might, if we do have this fault that I've shown down here where the X is, if that's a phase to ground fault, this winding down here, this winding right here, it has the ability to pass zero sequence current because it has a ground source with that ground on it. And because of that, we may want to have a ground overcurrent, either instantaneous, as I show here as a 50G, or some sort of a time overcurrent to provide backup protection for those ground overcurrents. Likewise, I mentioned earlier that we may not operate for all of the ground faults with the differential. So one of the things that we can also do is create a ground differential between this CT here and this CT here, so that forms a ground differential zone of protection with the restricted ground fault element. Now, the restricted ground fault element, basically what it's doing is it's comparing the 3I0 from the phase CTs down here, and it's comparing that to the measured ground current. And that's what that dude's doing. And then we're probably going to want some voltage in power metering. We may want some directional elements. If we trip a transformer, it's probably not a temporary fault. So we probably want to lock that out. That can be done with an external lockout relay, or it can be done with a lockout built into a microprocessor-based relay. And then for larger transformers, we have the potential for some abnormal conditions. Now, a through fault is an abnormal condition too, but when I talk about abnormal conditions, what I really talk about is abnormal operating conditions of the power system. So a 59 is an overvoltage, and a 24 is a volts per hertz. And if we have that sort of scenario, we can damage the transformer. An overvoltage works the same way almost as a volts per hertz or overexcitation, because overexcitation is given by volts per hertz. So if the voltage gets too high or the frequency gets too low, we can overexcite the transformer, cause extra heating in the transformer, and damage it. And so that's what that 24 element there is for, which is volts per hertz or overexcitation protection, and the 59 element, which is an overvoltage. Now, everything that I've marked up so far has been around this 2-winding transformer. Sorry about that, guys, especially to my co-presenters. We're having some electrical storms here in East Tennessee. And those electrical storms just knocked out my internet temporarily. So again, my apologies. My apologies for that. Hopefully that's the last of those that we see. Hopefully that's the last loud clap of thunder that we have, followed by me dropping and leaving 50 attendees in the lurch, and all my co-presenters sweating. Eduardo, just as a sanity check, you are hearing me, aren't you?
Yes, we're hearing you, Terry.
Okay. Thank you. Thank you. Thank you, Mike. Okay.
Yes, Terry, you're good.
Okay. Okay. Bear with me. Okay. So the other thing that we should mention here at this point also is what I've talked about so far is a 2-winding transformer. And in the application example that we're going to deal with in a few minutes towards the end of the presentation, we can do, a lot of transformers will have more than one winding. So with the 845 that I'm actually going to show settings for, with the 845 that I'm actually going to show settings for, we can have a 3-winding transformer like I show here. Now the same things apply to this 3-winding transformer. The same sort of protection schemes still apply. The only real key difference that we have on this 3-winding transformer is that our differential scheme is going to be somewhat different. Now our differential scheme encompasses both of these low side breakers because that's where our CTs are. Likewise, it's going to end at the high side breaker up there. So our differential scheme looks more like this. Okay. So the 845 relay that we'll talk about settings on in a few moments, it can protect up to a 3-winding transformer, like the transformer we just saw. And so typical protective functions that are available inside of it, it's going to have the, there we go, I lost my pointer. It's going to have the 87T here. So that's the transformer differential. It's going to be one of the most important things that we have. It's also going to have the overcurrent elements.
it's going to have the overcurrent elements that we're looking for, both ground and phase overcurrent elements over here. And then some of the abnormal operating condition functions that we've talked about also, like overfrequency, underfrequency, a voltage element, as well as the volts per hertz element that we mentioned also. So some of these other, those are the most important applications that we'll have. The other applications that are sort of shown there are some of the ancillary things that we might use on special applications. Now, one of the key differences between the UR and the 8 series relay, and the UR is a different family of relays than the 8S, is that the UR relay, there are 2 transformer protection relays available in that family. One of them is the T35, the other one is the T60. And because of the modular nature of the UR, we can do some different things with the T35 and the T60. Specifically, we can protect transformers that are larger than just a 3-winding transformer. So actually protect with the T35 and the T60 up to a 6-winding transformer. Now, it is rare to find a real legitimate 6-winding transformer in the wild, right? They do exist, particularly they exist more in the realm of a 5-winding transformer that is serving a drive. But for some of the other applications, the UR gives us some flexibility to model a larger bus or a larger protection zone as a transformer. So, for example, what we can do with this scenario here is if we can make the transformer differential zone from this CT all the way through these CTs. And what we can do then is we can model this as a 1, 2, 3, 4, 5, 6-winding transformer and include the bus in the transformer differential zone. Now, when we talk about restraint differential and slope differential characteristic here in a couple of slides, this will give us a lot better restraint quantities, because if we actually have a fault here and we can feed currents in this direction, for example, by modeling this bus as a 6-winding transformer, it gives us better restraint and better ability to restrain for that through fault, even if we have CT saturation. So for these conditions like this, the UR lets us model a larger area as a multi-winding transformer rather than what it actually is. So this transformer here, even though it's a 2-winding transformer, if I model those 6 CT inputs as 6 separate windings, I get much better protection, and that's something that's available in the UR relay. Okay, so let's talk about some of the external faults and stressors on transformers. There are certain things that will stress the transformer. If we have a downstream fault, that is going to put stress on the transformer. We would rather the downstream protective devices that are meant to trip that fault trip, so we want to coordinate with them. We still want to trip in a timely manner, right? So before we damage the transformer. We'll talk in a few moments about how we do that. We probably want to use over voltage. And again, part of the reason we want to use over voltage is to protect for an overexcitation of volts per hertz. So we either want to use volts per hertz, which is 24 element, or just a pure over voltage element. And so the over voltage conditions, they can be caused by transients. They can be caused especially if we're in a generation station, or even a radio fed distribution station. Under frequency, we're going to worry about it the same basic way. Overexcitation is given by volts per hertz. So if we go, since the frequency is in the denominator there, and it's at the bottom, we're going, if it goes low, we're going to overexcite the transformer. So we want to trip for that as well. There are some incipient faults that could cause us some problems as well. A lot of these are related to heat or other mechanical issues. So if we lose the fans or the pumps, or we've got blocked cooling, right? The radiators are blocked. The cooling for the radiators are blocked by dirt or debris or leaves or who knows what else. We probably want to trip our alarm from that. Now, we can't really do that with a relay from an electrical measurement, but we can do that from a hot spot temperature calculation, or not calculation, but actual measured hot spot temperature from the RTD. Okay. Another incipient fault that we could have is if we have this volts per hertz condition that I mentioned earlier. So the volts per hertz condition, the way that it creates damage is it creates an overexcitation condition. That overexcitation condition, what happens there is you will drive excitation currents and eddy currents into places that are not meant to have them, like the case of the transformer. That creates extra heating, and because that creates extra heating, it can eventually damage the transformer. So we want to trip for that condition. Now, the interesting thing about voltage overexcitation, overfluxing, is that because it's damaging the transformer by causing extra heating, it can take some time. So typical settings for that are around 1.1. So typically a transformer can have a 10% overexcitation is rated for that. But we can give it a long time delay before we actually trip because of the mechanism of the failure. Something that we cannot wait on is an overpressure condition. So if we have a turn-to-turn fault that's inside the transformer that's slowly burning, that turn-to-turn fault will create some gases. And those gases can cause pressure to accumulate, or they can cause the pressure to increase inside of the transformer. So there are a couple of protection mechanisms that we can employ for that. One of those is either a Buchholz relay or a sudden pressure relay. And it really depends on the design of the physical sort of design of the transformer as to which one of those you use. If the transformer has a conservator tank, so a conservator tank would be a big tank sitting up here with pipes down in there. If it's got that conservator tank, then it's going to have a Buchholz relay. If it doesn't have that conservator tank, it's probably got a nitrogen cabinet sitting here with a bottle of nitrogen. And if it has and that nitrogen tank keeps a nitrogen blanket on the top of the transformer up here. And those sort of transformers, they would have a sudden pressure relay sitting on the top of the transformer. Both of those relays should be wired such that those are both mechanical relays. They're not going to be a part of the microprocessor-based relay that I'm going to spend the bulk of my time talking about. But both of those relays should be wired to trip and isolate that transformer. Okay, so some of the most important elements that we really have are the restricted ground fault, transformer differential, and the instantaneous and timed phase and ground overcurrent. Now, what we employ will depend largely on the type of transformer we're using. So if we look at this particular transformer, this is a medium voltage to low voltage transformer at up to 2.5 MVA. Now, transformers of this size, they're largely disposable. When I say disposable, if you have damage to this transformer winding, it's probably not repairable. You probably are going to replace that transformer. And so because you're not really going to attempt to repair that transformer, what you don't see here is a transformer differential. What you see is an overcurrent and maybe a ground overcurrent. Now, if we look at the next transformer, This transformer, if you look at this size requirement is smaller than the 2.5 MVA that I see here. But what is different here is the voltage level of these transformers. This is medium voltage to medium voltage. So this is something like 13 kV to 4 kV. And in that case, that transformer is not really, it's not as replaceable as the previous trend. In the previous transformer, if we really look at this, this is something like 13 kV to 480 kV. This transformer may be sitting on your distribution utility's yard today, or something like this transformer may be sitting on that distribution utility's yard today. This transformer is a much longer lead time item. It's harder, and for that reason, it might be more repairable than replaceable. And so for that reason, we're going to roll the whole transformer into this transformer differential scheme. So our transformer differential scheme is going to encompass from that CT to that CT, include the entire transformer. On top of that, at this size, we've got the 63 device. And the 63 device is this sudden pressure relay that I was mentioning earlier. And so this is a relay, a mechanical relay that's mounted on the transformer itself. We're probably going to, if there is a source up in this area, right, then we're probably going to want to source a ground, or excuse me, a phase over current here, probably a ground over current here. Now, let's talk about the time over current protection. Now, time over current protection will be one of the, in addition to transformer differential, it'll be one of the most important protective elements we have on the transformer. We always spend so much time talking about transformer differential because we always assume that everybody understands and knows time over current. But it's worthwhile mentioning it briefly today and how we protect a transformer with a time over current element. Now, what you see here are these stacked time over current elements. So each one of these lines is a time over current element. So I've circled those lines there. Along the bottom axis down here, what you have along that bottom axis is multiples of the pickup setting. So that's multiples of pickup setting. And then along the axis to the left is the time to trip in seconds. And the curve shape is a choice of setting. So the curve choice is a choice of setting. That setting describes what the curve will look like, how steep it is, basically. So that's one of the most important settings. There's really three settings associated with the time over current: the curve shape, and the pickup. And the pickup will decide, that will determine where you start timing this, where the pickup value is. If this was an electromechanical relay, the pickup value would be the current at which the disc on that electromechanical relay just started to move. So that's the next setting. The other setting is a time dial setting. And the time dial setting effectively serves to move those curves up and down. So a larger time dial means the curve will take longer to trip. So you can think of this as time dial settings. Time dial settings move the curve up and down, and the pickup setting can move it right or left. And then the shape would just basically describe the shape of the curve. When we start coordinating these time over current curves for a transformer, a lot of the same rules of time coordination still apply. So if we look at this slide, I'm showing an actual time current curve for a transformer. So my transformer is right here. So let me circle him. Transformer sitting here. And we've got a breaker up here at the top right here. And we've got a overcurrent element sitting right here. Now, if we have a fault down here at panel board 2, we've got a fault down there at panel board 2, we would much rather the protection trip on the secondary of the transformer rather than tripping up at on the primary on the top, right? So in fact, let's change this scenario that I'm describing, and instead of putting my fault right here on the secondary of the transformer, let's put my fault down here on panel board 2. Now, what we'd rather happen there is we'd rather a breaker trip on panel board 2 rather than tripping this transformer offline. So what we want to do is we want to time coordinate the operation of our overcurrents. So the way we do that is we sort of stack these overcurrents up such that the device that is closest to the fault will trip first. So in this case, we've done that. And so there's a limit on how high, though, we can set the 51 element protecting the transformer. And that limit is given here. So this blue curve that I show right here, this blue curve is the transformer damage curve. And so we do not want to get into that transformer damage curve. We want to trip before we get into that curve. So what we're going to do is we're going to choose a green curve, like this one that I show here, that is our protective element. This is going to be our 51 element or time overcurrent element that is coordinating the transformer damage curve. It also coordinates with the downstream devices so that we meet the downstream devices before the transformer, this transformer overcurrent. But at the same time, we have coordination between the transformer damage and the transformer overcurrent. So in other words, we're going to operate the transformer overcurrent before we infringe on the transformer damage curve. Now,
Hey Terry.
Transformer overcurrent, you can.
Sorry to interrupt you, but the screen slides are a bit lagging. So could you avoid going back and forth on the screens and maybe drawing on them, because it's very lagging on our end, if possible.
Okay. Okay. Give me just a second. Let's see if I can fix that. Okay, guys. Okay. Yeah, I had to take care of something. I think the thunderstorm caused me some additional problems, but nonetheless, I think I've got this fixed. Let me test it. You guys are seeing this in a much quicker fashion now. Good.
Yes, yes.
Okay, yeah, and thanks for telling me that, Mike. So what I've drawn here in the red, this is an instantaneous overcurrent. So this is an instantaneous overcurrent, but I need to set this as a definite time overcurrent. And so basically, anytime my current is above 9 times, pick up here, or 9 times, let's see, 90 KA or so, I've got a flat characteristic. So I've set the instantaneous overcurrent flat because I've set it as a definite time element. So anytime it's over about 900 amps, it looks like it's going to operate instantaneously with a time delay, and that time delay is about
about 110 milliseconds or so. Now, I set this time delay because of this little dot here, right? And what that little dot right there is that is the transformer inrush. So when I energize this transformer, there's going to be a lot of current that flows into that transformer to magnetize the transformer, and that will look like differential current. All right, it'll look like differential current if I don't block that, but it'll also look like an overcurrent because it really is. It is an overcurrent event, but it is an inrush event. So to keep the transformer from tripping offline for that, I've got to set my time delay on my instantaneous element long enough to coordinate with that inrush. And so the inrush is right here, this little dot that I've drawn the arrow to, and it's a time and a current. Now, all of this graph that I've shown here, all of this is probably coming from something like Easy Power or ETAP. Either one of those software packages, as well as many others, will give you a transformer, a typical transformer damage curve, like we see here with this blue curve right here, right? And it'll also give you the inrush. And then it's up to you then to pick the transformer overcurrent, time dial, pickup, those sort of things that will coordinate with both the inrush conditions, the downstream devices, and that transformer damage curve. Okay. So the next element we probably ought to talk about is the transformer differential. Transformer differential is going to be the fastest element. The great thing about the transformer differential is that it doesn't overreach. Its zone of protection goes from this CT to this CT, right? And should encompass the transformer there. Now, the overcurrent, it would inherently overreach because it would overreach the transformer protection zone and go well beyond the next protective device. And because it overreaches, that's why we have to time coordinate it. That's why it's a time overcurrent element. It's also why I have these time current characteristic curves where we stack these elements up. So that time coordination will slow things down. There's no intentional delay that we have to add on a transformer differential because it has a defined zone of protection, which is, as I've shown in this box here, from that CT on the left to that CT on the right. Now, the way that transformer differential is going to work is it's going to basically do a vector sum of the compensated currents. So if we ignore the fact that we've got different voltage levels and different current levels on this transformer, we also got a phase shift on this transformer. You know, if we have 1 per unit of current flowing in here, and we got 1 per unit of current flowing out here, that looks like 1 per unit at 0 degrees into the relay here. And then that looks like 1 per unit at 180 degrees out of the relay there. Those two vectorially sum to 0. 1 at 0, 1 at 180, they vectorially sum to 0. Now, if I actually have a fault here, one of two things happen. Oops, sorry, I hit my mouse wrong. So if I actually have a fault inside the transformer differential zone, one of two things happen. Either I have fault current flowing here with 0 fault current there, or I've got fault current flowing in here and fault current flowing in here. So this scenario, that looks something like 1 per unit at 0 degrees plus 0, and that's a differential that would cause it to operate. If we take this scenario on the bottom, you know, that looks like 1 per unit at 0 degrees and 1 per unit at a 0 degrees. Those vectorially sum to 2. Those vectorially sum to 2, and that would cause us to operate. So one of the problems, though, with differential is that the differentials are relying on CTs, and CTs are inherently not perfect devices. So instead of 1 per unit at 0 degrees, and 1 per unit at 180 degrees, there will be some error in that. There will be some error because of the CTs, because the CTs will have some excitation losses. They will not be perfect. So the way that we can accommodate the error in the CTs is with a slope differential characteristic. Now, what I show on this graph here is that slope differential characteristic. And so along the bottom axis here is a restraint current, and the restraint current will be the maximum of those two currents flowing into the relay, in the two currents from the previous example. The differential current, which is along this axis, will be the vector sum of those currents. Now, with settings inside the relay, we build this slope differential characteristic that is shown with this red line there. Everything below that slope differential characteristic is in the block region, or the restraint region, the region where the relay does not operate. If we are above that line, then we are in the operate region, and we're going to trip or operate. So imagine my example, and let's say because we've got some imperfect CTs, instead of being at 1 per unit at 0 degrees and 1 per unit at 180 degrees, we are at 1 per unit at 0 degrees and 0.9 per unit at 180 degrees. Well, that gives us a differential of 0.1. So we'll probably sit somewhere in here. But remember, our restraint is the maximum of those two, which would be 1. So that might be here. So that's going to put us below this line here. Now, and that gets us into the block region, right, where we don't operate. If we are in the scenario where we don't have a source on the downstream side and we have a fault inside the generator or inside of the transformer, then that looks like 1 per unit at 0 degrees, and 0, that looks like 1 per unit sitting up here, and 1 per unit. So we're right here and we operate. Likewise, if we have a contributor on both sides, that looks like 1 per unit at 0 degrees and 1 per unit at 0 degrees, then we're up here at 2 differential, and we're up in this range where we can operate right here. So again, we're going to operate. So the slope differential characteristic that we show there is made up of settings inside the relay. So the pertinent settings are the pickup, a slope 1, a slope 2, and a breakpoint 1 and a breakpoint 2. So bear with me, let me clean this slide up just a moment. So the first setting is a pickup. We see the pickup in blue over here to the far left. Now, the pickup basically is the setting that the differential has to be, the value of differential has to be greater than that pickup setting before the element will ever operate. So that defines this point over here on the far right, where we first intersect that axis of differential, right? Now, the next setting would be the slope 2, slope 1. And slope 1 is set as a percentage. And it is what percentage of differential do we have to have of the restraint to actually operate? So typical transformer settings have a differential setting on the low slope of around 35%. So in our example, if we have a restraint of 1 per unit, then we would need a differential of 0.35 to operate, to be up in above this line. Now, breakpoint 1 is where we transition from the low slope to the upper slope. Now, breakpoint 1, breakpoint 2 on transformer relays, good settings there are around somewhere around 2 for breakpoint 1 and 4 for breakpoint 2. And above breakpoint 2, this is where we're going to try to accommodate heavy CT saturation. And so, that heavy CT saturation might come when we have really large faults, really large through faults. And so for that reason, we can have a very high slope setting for above breakpoint too. So typical slope settings there around 65, 75%. Okay. So on this 3-winding transformer that I mentioned earlier, basically what we're going to do is we're going to take the differential, which would be along that axis, up and down axis on the left. That is going to be a compensated vector sum of all the currents connected to the zone of protection. Compensated, I'll talk about what that means in the next couple of slides, but basically what we're doing by compensating for that is we're accounting for the fact that there is phase shift across this transformer, and also the voltage levels are different across the transformer. Restraint, again, it is going to be the maximum of those compensated values. And then the slope is actually the ratio of the differential to the restraint. And it's expressed as a percentage, and that's why that 100 is there. So let's talk about compensation. If we look at this particular transformer, we have a Y on the H winding side, and we have a delta on the X winding side. So this particular transformer has a 30-degree phase shift. Now what that means is that the little a lags the big A by 30 degrees. And that's what we sort of express over here. Here's the big A, here's the little a, and he's lagging by 30 degrees. Now the way that this actually happens is that this transformer here, or these windings here, are exactly in phase with the other windings there. So if we have an A that's sitting right here, what's coming out right here is exactly in phase with what's right there. But our CTs are going to be right here. So what is going to go into the CTs actually, and also the bushing is probably sitting, right here. What's also coming out of the bushing is going to be this A minus what we see on C. So if we take the C over here and superimpose him on the negative of C, then that's where we get that 30-degree phase shift. And so that's where that comes about. Now that's going to we have to be able to accommodate that phase shift in our transformer differential. Otherwise that 30-degree phase shift is going to cause us differential current. So we do that with phase compensation. One of the other ways we need to compensate this is magnitude compensation. So imagine if this is a 13.8 kV to 138 kV transformer. So let's say instead of 1 per unit here, let's say this is 13.8, right? And this is 138 over on this side. Well, if I have 1 amp flowing out that 13.8 kV transformer, that means I've probably got, 1 amp flowing out of the 138 kV winding. It means I've probably got 10 amps flowing into the 13.8 kV winding, right? So I've got this transformation ratio I have to deal with. If I've got 100 per unit here and 20 per unit here, I've got 1 per unit here and 5 per unit here. So I've got to do magnitude compensation because of the voltage transformation of the transformer. Also means that there is going to be a different current flowing into the X windings, or into the H windings versus the X winding. Another thing that I really need to deal with also is zero sequence removal. So if I look at this transformer here, this transformer has a delta to Y conversion on it. So let's say this is a generating station and this is my generator sitting right up here. And that Y connected winding is sitting out connected to my transmission system. Now, the reason we have a Y connected, and this is a grounded Y. I'm not sure it is a grounded Y, but let's assume that it's a grounded Y. The reason I've got that grounded Y connected to the transmission system is so that I can sense ground faults on the transmission system. Now that delta to Y conversion, it blocks that zero sequence current. That's great because I do occasionally have ground faults out on the transmission system, but I want to block that zero sequence current from my generator. I don't want that to damage my generator. And I can block that with that delta to Y conversion. The problem that causes me though, is that I can pass zero sequence, if my CTs are here, right? And my CTs are here. Oh, I can pass zero sequence current through this set of CTs on the Y connected winding, but I can't pass it through the other side on the delta connected winding on the generator side. So that's going to cause me to miss op if I don't remove that zero sequence current in some way. Now, the way that we did that back in the day with old electromechanical relays is we would wire the Y side CTs Okay, we'd wire the Y side CTs in delta. Y side CTs wired in delta would block the zero sequence current, but it would also do something else for us. It would get us that phase shift back. Now, in a modern microprocessor-based relay, we don't have to do that. The reason we don't have to do that is because a modern microprocessor-based relay is really good at doing calculations. And so what it can do is it can do that zero sequence compensation and the phase compensation inside of the relay. So we don't have to. So we don't have to. We can wire both sets of CTs in Y. Okay. So now, as we look at typical transformer connections, what I show on the screen now is transformer connections for a UR relay. So this is a 3-winding transformer. And I always like to say that CT polarity doesn't really matter as long as it's right. So what you can see is since the CTs, the polarity on the CTs is shown away from the zone of protection, away from the transformer, we can wire CT polarity to the relay polarity. Now what that means is instead of seeing this as a 30-degree phase shift, what that means is we will see this as a 210-degree phase shift, because we'll see that 30-degree phase shift plus an additional 30 degrees. Okay, so these are the connections. What I've highlighted here is the connections for the 3 windings. So these are the CT connections, and then we have some options on our actual VT connections, either a Y connected VTs or a delta connected VTs. Now, as we look at this compensation of the phase shift, we can really think about this in one of 2 ways.
So there is typically a 30-degree phase shift associated with the transformer itself. And that's what we see on this transformer primary phasor diagram here. On the CT secondary currents, this is going to have the 210-degree phase shift that I mentioned earlier. Now, this is because of the way that we're wiring it. We're seeing current flowing into the zone of protection, coming into the relay, and it's flowing out of the relay as it's flowing out of the zone of protection. So that gives us a 180-degree phase shift plus the 30-degree phase shift of the transformer. So what we expect to see our secondary currents be is at minus 210 degrees. Now, the way that we actually set this up, and these are settings from an 845 relay. So the 845 is the 8 series relays, the 8 family of relays that have transformer protection in it. So we need to set up the 3 windings.
Terry, sorry to interrupt you. There's a little bit of a lag on the slides again.
Okay. Like I said, my apologies, guys. I'm having some electrical storms, which is causing my internet to give me some problems. We can either, let me try this one more time. Okay, guys, I'm back. Maybe what I should do is just every time I hear a lightning strike outside, maybe I should just stop for a few minutes. But nonetheless, so here's inside of the 845 relay. This is where I'm going to set up my CTs, right? So I'm going to set my 3 windings. And this is also where I'm going to set the CT ratio. Now, typically, we're not going to have CT ratios all be 500 to 5. Probably not going to have the ground CT ratio be the same as the phase either. But once I set that up, now I need to tell the relay things about my transformer in general, and I also need to tell it things about the winding. So what I'm going to tell it, let's see here. So I set this. What I'm going to tell it is I want to do internal compensation, right? So what internal compensation means is it's telling the relay that I am not using CT connections. I am not using CT connections to compensate for phase shift and zero sequence removal. What I'm actually going to do is I'm going to use the internals of the relay to do that sort of compensation. And the way that I'm going to do that compensation is with this setting here, right? And this setting here. So the setting of angle with respect to winding 1 is it is asking me how much does this winding, in this particular case I've highlighted winding 2, how much does winding 2 lag winding 1? And so since this is a 30-degree lagging transformer, it should be set to 30-degree lag. And then the grounding setting, it's asking me, is this winding, is it have a ground source inside of the zone of protection? So a ground source is a grounded winding, for example. So this particular winding is set in delta, so it's not got a ground source within zone. The winding 1 above it, you don't see the angle with respect to on it because it's angle with respect to winding 1. And it's always going to be 0 in with respect to itself.
it's set in Y, and this must be a grounded Y because it's set within zone. Now, that angle with respect to winding 1 and the grounding, this is how the relay does phase compensation and zero sequence removal. So the way that it does this, we can think of it doing this in one of two ways. One of the ways is the simpler way, and we could say that it magically removes the zero sequence current and shifts the currents by 30 degrees. So that instead of at 210, it's sort of the calculation happens at minus 180. That is one way we can think of it. That is the simplistic way we can think of it. The way that the relay actually does the compensation is based on these two settings, the angle with respect to and the grounding, is it calculates a compensation matrix. And that compensation matrix is then applied to the measured currents to create a compensated current. So a compensation matrix usually looks something like A phase current is going to be equal to like 1 over the square root of 3 times A phase current that's measured minus 1 over square root of 3 of B phase current that's measured. The way that calculation matrix is calculated is based on how the transformer is actually wired. So it's using a combination of the currents to get that phase shift back. The other settings that are important are the nominal phase-to-phase voltage of the actual windings. So in this case, this is a 230 kV to a 13.8 kV transformer. And it's basically using that ratio to do magnitude compensation. So I can't do this math in my head, 238 and 113.8. But if this were a 138 kV to 13.8 kV, I could do that math in my head. The magnitude compensation factor would be 10. And it would multiply the 130, it would multiply after we account for the, the ratio difference of the CTs, it would multiply the 138 kV currents times 10 to take care of magnitude compensation. Okay, and then once I've done that, my next step is to set up the differential. So in setting up the differential, what I'm going to do is I'm going to build this characteristic on the right. The first thing I'm going to do, is I'm going to set it to trip. This is an 845. And then my pickup here is my first setting. So again, that is the point, that is the differential has to be greater than that value to operate. So I've set my pickup at 0.2 times CT. That is a typical setting for my pickup value. Slope 1, remember, God damn it. Okay. Slope 1 here is set here at 25%. So that means my differential has to be above 25% of my restraint to operate. Breakpoint 1 here is set at 1.5. So slope 1 is the slope less than breakpoint 1. Breakpoint 2 is set here at 4, and all of these are fairly typical values of differential. So my slope above breakpoint 2, I can set that much higher because this is for heavy. This is to keep me restrained for heavy through faults. So I've set that to about 95%. The other settings that are important here are, I mentioned earlier that when we first energize this transformer, we're going to have a lot of inrush current. So the settings that are important there are the way that I block or for inhibit for inrush. So typical settings are second harmonic blocking 20%. Now, we'll see in a few minutes that this inhibit mode of per phase is not a good idea. In fact, that I probably want to set the inhibit mode to either average or 2 out of 3 rather than the per phase that I see here. Okay, so that's settings for an 845. If I'm doing this inside of a UR relay, I'm doing basically the same thing, but there are a few extra steps. So inside of the UR, I'm going to do this. I'm going to set my CTs for all of my CTs that are connected to the relays. The extra step that I'm going to have to take inside the UR is I'm going to have to configure signal sources. So by configuring signal sources, I'm telling the relay where to get its currents for to source protection. So I'm calling source 1 the F1, source 2 F5, and it doesn't look like I'm using source 3 in this particular example. This particular transformer is going to be a 2-winding transformer, so I'm going to model it as a 2-winding transformer. And again, I'm going to do a phase compensation as internal because I want the relay to do phase compensation and zero sequence removal rather than doing that with CT. The other option for that phase compensation is external with CTs. If I'm in a retrofit application and I cannot rewire my CTs, then I probably want to use external with CTs. And then once I've done that, I set my windings almost exactly like I do with the 845. I've got a phase-to-phase voltage setting. This is the transformer phase-to-phase voltage settings. I set that for each of the windings. Doing that for each of the windings allows the relay to then perform magnitude compensation. The next 2 settings that matter are the grounding and the angle with respect to. So grounding again means, is there a ground source within the zone of protection? So most likely that delta does not have a ground source in the zone of protection, so it's set to not within zone. And the Y looks like it's solidly grounded, so I'm going to set that within zone. And winding 2 lags winding 1 by 30 degrees. So the angle with respect to winding 1 is minus 30 degrees. Angle with respect to itself on winding 1 should always be 0. Okay. So this is what this looks like on the actual settings. Okay. So again, this setting of zero sequence removal, this is the sort of grounding. Now, the question you may ask is, well, why do you even have this setting? If we have to tell the relay what the connection is, either Y or delta, why should delta have the ability to be within zone or not within zone? And this is sort of important because if we can have a grounding bank that is also inside of the transformer differential zone of protection, that grounding bank will also serve as a ground source. And if we have that configuration, we would need to have grounding set to within zone, even though it's a delta connected winding. But in most instances, the delta does not have a ground source, so we're going to set that not within zone. And if the Y is grounded, we have to set that within zone. Okay, so as I said earlier, the slope differential characteristic takes care of CT inaccuracies. So the first characteristic is this low region. And this low region really is meant to help us out for steady state conditions. So sort of when we're in the steady state, you know, we expect to have 1 at 0 degrees and 1 at 180 degrees. Now we don't really actually have that because of the CT inaccuracies. You know, so we expect to be some small differential current, very small, and some small level of restraint current. So we can have tighter settings down in this lower region because really all we're really meaning to do here is to provide some restraint for CT inaccuracies in the steady state. Now the upper region, up in the high region, this is really meant to provide security for a really heavy through fault. So let's imagine a really strong through fault. And so instead of our steady state condition at 1 at 0 degrees and 1 at 180 degrees, this looks like 1, or it looks like 10 at 0 degrees. And let's assume our other CT saturated. And instead of giving us 10 at 180 degrees, that looks more like 6 at 180 degrees. Well, the vector sum of 10 and 6 is 4. So that'd give us a differential current right here. But remember, our restraint is the largest of those two quantities, which is 10. So that would give us a characteristic right here, right? So we would be right here inside of the restraining or the block region. So we'd be below the curve. Now, if we actually legitimately struck a fault, inside of the transformer differential zone, instead of moving this characteristic like we show here, we'd move straight in, right? So it'd be 10 per unit at 0 degrees, for example. So we'd move, way up into here and we'd operate. So really the challenge with transformer differential, and really the challenge with all differential, is not getting it to operate for a legitimate fault. It's more a challenge around preventing it from operating for a very heavy through fault that causes a lot of CT saturation. Okay, so I've covered some of this. An additional check that we place on just about all of our modern firmware versions of relays is an additional directional check, as well as the differential characteristic. So if I have an internal fault, so what that means is all of the fault current is inside of the zone of protection. All of my fault currents will be in the same direction. So they'll be either 0 if there's no source for them, or they will be flowing into the zone of protection, which will look like 1 per unit at 0 degrees and 1 per unit at 0 degrees. And so when I see that, the relay can set a directional flag. It'll set that directional flag of 1. Now, if I have an external fault, the relay will set a directional flag of 0. And so with an external fault, at least one of the currents that's large enough to be a contributor is 180 degrees away, or it's in the opposite direction of the other relays. It doesn't actually have to be exactly 180 degrees. There's some tolerance built into the algorithm, but it's going to be close to 180. And if that's the case, the directional flag is 0. So in modern firmware devices, what we did was we added some extra security measures. So what those extra security measures do is, if the directional flag is set and we're in the low region, we can operate, right? If we're in the upper region, which is this region up in here, we've got to do the directional check or a saturation check. Okay. So if I get an external fault with saturation, what I really expect to have happen is that the relay takes this characteristic like this. And so that characteristic like that looks more like a saturation characteristic. Okay, so let's move on and talk about harmonic restraint. So I mentioned earlier that when we first energize the transformer, we will create a lot of inrush current. So that inrush current, since we're just energizing one side of the transformer, that inrush current can look like a lot of differential current, and we would operate for that unless we take some mechanism to prevent operation, right? So, excuse me. So the way we used to do this with electromechanical relays is the electromechanical relays had a filter that was tuned to the second harmonic, basically 120 hertz. Now, as it turns out, when we have these inrush events, these inrush events create a lot of second harmonic content on the current circuits. And those electromechanical relays with a filter tuned to the second harmonic at 20 hertz, that filter could then filter out that second harmonic content and use that to provide restraining or opening torque on the electromechanical relay. So in a microprocessor-based relay, we can do this with calculations. Now, the way we do this with calculations inside the microprocessor-based relay is we're still looking at the second harmonic, but we're looking at the second harmonic as a percentage of the fundamental, and that can be a setting. Now, in the electromechanical world, it was set that if the second harmonic component was greater than 20% of the differential fundamental component, that 20% would provide enough restraining torque to keep the disc from turning and keep it open. And so inside of an electromechanical relay, we can set at what level we want to keep it open, we want to block for. And so, typical settings are around 20%. Now, what we find though with modern transformers is that modern transformers will create a inrush characteristic very much like what we see on the screen to the right. So these waveforms here, these waveforms are the actual currents. But if we look at these traces here, what those traces at the bottom are the magnitudes of the second harmonic. And you can see in the graph data here that we drop below that 20% threshold. So in a modern microprocessor-based relay, there's a phenomenon where we might produce a lot of second harmonic content for a few cycles, and it may drop down significantly, as it has in this case, where the magnitude of A phase dropped down to 9.9%, and the magnitude of B phase dropped down to 13.6%, and C phase is at 38.5%. So because of that, there's three inrush inhibit modes. So one of those modes is per phase, and that's what I showed on the slide earlier in the presentation, and I said that's probably not a good idea. And that's how electromechanical relays operated. Because they were phase segregated relays, they operated per phase. We don't want to do that, because if we did that on this particular transformer, we'd trip on A and B phase, because A and B phase both drop below that 20% value. So other choices are 2 out of 3 or average. Now, on this particular transformer, if we'd chosen 2 out of 3, we don't have 2 out of 3, so again, we'd misoperate. Now, if we chose average, the average of these three is just a little bit over 60, and we would restrain. So typically, the better value to set that at is average. Don't ever set that to per phase unless you want it to misoperate. The only reason that we give you per phase as a choice is because we're mimicking what is available in electromechanical relays. I don't think that's a good setting to give you, but nonetheless, that's the reason we do it, and that's the reason you shouldn't do it, right? You should set that to per phase. So let's look at what that, I thought I had a better slide on that. Here we go. Yeah, so you really want to set that to average, not per phase. And sometimes, most of the time, you can get by with 2 out of 3, but average is a better way to set that. Okay. So, as promised, I said I would go through an application example. So let's go through this application example. So here is my transformer. I've got a 3-winding transformer. And it looks like this guy is delta Y30, Y30. So that means the X1 and the Y1 are lagging the H1 by 30 degrees. I've got a H winding. It looks like it's 138 kV. It's 600 to 5. 600 to 5 is the ratio. X and the Y, they're both 400 to 5. That's good. They're both grounded because they're Y, it looks like. And their ground CT is 400 to 5. And one of them is a 13.8 kV winding, and one of them is a 4.16 kV winding. Okay. So let's, instead of going through PowerPoints, because I'm sure everyone is sick to death of seeing PowerPoints, let's set this up. Let me basically cheat here, and let me move my screen over here so I can see what that transformer really was. And let's set this up in 8 series setup, right? So I've added an 845 relay to my offline window here. This is 8 series setup. So I'm gonna set this transformer up in this 845 relay. Now there's 2 sections here. There's an online window up here where my cursor's at right now. That online window, that is basically the relays I am connected to. So I'm not connected to any relays now, so I'm going to close that. Now this is my offline window. So these are the settings files that I've added to my laptop. So the relay settings file I'm going to work with, this is this 845 training CID here. So let me expand it and we'll start setting this dude up. So it's got to build the CID file. It's got to do some things. So the first thing that we really need to do is probably set up some system settings. So I'm going to expand system here, and I'm going to expand current sensing, and these are the default settings. Now, turns out I can name these CT banks. There's nothing wrong with winding 1, winding 2, or winding K1 or J1 or K2. Those are actually where we wire those to the input of the relay. But I'm going to name them something that makes more sense because it's just going to help me out. So I'm going to change this winding 1 to H, winding J1, right? Now remember that one was set to 600 to 5. So I'm going to change that to 600 to 5. Okay. Now, that was the delta winding, so it didn't have a ground CT. So I'm not going to monkey with the ground CT. I'm going to leave that as the default settings. My next winding, I'm going to set that as the X winding. Wire that to K1. And remember that one had a 4,000 to 5 CT ratio. Uh-oh, I did something wrong. Oh, I entered the wrong value. I tried to set that at 20,000. I've never seen a 20,000 amp CT ratio, but that should be 4,000, right? All right. Now the ground CT, the primary, is 400. So I'm going to set that to 400. So this must be my Y winding. So I'm going to rename that as Y winding. I don't have to rename these windings, but it just makes it easier for me in just a moment. So again, that one's 4,000 to 5. So the primary is 4,000. The ground CT was 400. So I'm going to set that primary as 400. Okay, let's just leave that sitting there. Now, the next thing I probably need to do is to set my transformer and set up my transformer. So let's set up my transformer. So I'm going to double click here. I'm going to do a transformer setup. And then now I'm going to set up these 3 windings. Okay. So it's going to ask me what my reference winding is. Now, when it's asking me what my reference winding is, it's saying, what do you want all of your settings referenced to? Now, I could choose any of my windings to be my reference winding. The default is always winding 1. I'm going to leave that at the default. Now, remember, my choices here on phase compensation was either internal with software or external with CTs. So external with CTs means that I'm going to wire my Y side CTs in delta and my delta side CTs in Y, and that's going to take care of my phase shift and zero sequence compensation with the CT connections. That is a much difficult design job, so I'm going to wire both sides of my CTs in Y, my high side, my low, my H, my X, my Y, doesn't matter if it's delta or Y connected. I'm going to wire them all in Y, and I'm going to tell the relay to do the compensation internally based on my settings below. Okay. These next few settings, this load loss at rated load, rating winder, temperature, all of these settings deal with a loss of a transformer aging factor or a transformer loss of life factor on the transformer. This is based on some work from the IEEE, and the IEEE said, you know, based on these values and the measured current, we can calculate how fast the transformer is aging. This is sort of a monitoring condition. It is not necessary to enter those settings in the transformer differential. The ones that really matter here for the transformer differential are the reference winding and phase compensation. The rest of these don't matter as much. This energization winding source, that's asking me how am I typically going to energize this transformer, and I'm going to energize it with the J1 winding. Okay, now my next few settings for winding 1, 2, and 3, those are all dealing with the transformer windings themselves. So this is where I'm going to add settings to take care of phase compensation, zero sequence removal, and magnitude compensation. So let's go to winding 1. So winding 1 was the H winding, right? I know that because that screen's still open right there. So that particular winding is not on my diagram. It doesn't say what the MVA rating is. That's a very important thing. So let's say this is a 50 MVA winding, right? So winding 1 is 50 MVA. Now, my nominal phase voltage on winding 1, that was the H winding, and it was 138 kV. Now that setting again, that nominal phase voltage setting is very important because that setting is going to be used for magnitude compensation. So I'm going to set that to 138. Now, my next setting is the actual connection. Now that particular connection is the delta connections. So I'm going to say that one is delta. That is asking about the winding setting itself, and it is delta. That delta connection does not have a ground source inside of the zone of protection. So I'm going to leave that with not within zone. This winding resistance here, again, this is used in that transformer loss of life calculation. It is unnecessary for the transformer differential. So winding 2, let's say it's a 25 MVA winding. And winding 2, that was the X winding. It had a voltage rating of 13.8 kV. So I'm going to set that for 13.8 kV. Its connection, it is a Y-connected winding, and it was lagging the H winding by 30 degrees, right? So my choices here are integer multiples of 30 degrees. I'm going to choose the first choice, which is 30-degree lag. Now, what that means is that the X winding is lagging the H winding by 30 degrees. Now, if I were to look at this on metering quantities inside the relay, what I would expect to see on the relay, though, because of the way we've wired it and the way that we have to wire it, I would expect the H to be at 0 degrees, A phase on H, for example, to be at 0 degrees, and I would expect A phase on this winding to be at minus 210. So that's 180 degrees because of the way that we're wiring it, plus the 30-degree phase shift. So that's at minus 210. We set it, though, with the actual winding, which is minus 30 degrees. So the grounding here, it is a solidly grounded Y winding. So we're going to say that is within zone. And that gets winding 2. So the only thing left now is our winding 3. So it's a 25 MVA winding also. Its voltage level is 4.16 kV. Its connection is also Y, and it also lags by 30 degrees. It's solidly grounded, so I'm going to say it is within zone, right? So I'm going to save that by clicking on the save button at the top. I'm remiss in that I haven't saved my CT settings yet, so I'm going to save those as well. Okay. So now what I've done is I have set my CTs, I've set my windings on my transformer, and those settings are allow the relay to do phase compensation, zero sequence removal, and magnitude compensation. Now the only thing left for me to do is to set my transformer differential. So let's do that. So to do that, I'm going to launch the protection summary here. And it's going to launch the first element on the protection summary is the transformer percent differential. If I click on the function there, it brings me to the settings for my transformer differential. Now, first thing I really need to make sure that I do is I set this to trip. Now, by setting it to trip, that means that it is going to operate the dedicated trip output of the relay. So that means if I have the breaker, the lockout, whatever I want to trip, wired to that dedicated trip output contact, when this element operates, it's going to trip. Now, pickup setting, remember the pickup setting is that that value of differential. We have to be greater than this value of differential before we'll ever operate. So a pretty typical value is around 0.2 times CT. So I'm going to leave that as default. The default value of slope 1 is around 25, is 25%. I prefer a little bit steeper slope, so I'm going to set that to 35%. Breakpoint 1, breakpoint 2 are 1.5 and 4. Now, I'm going to leave them as is, and these are good settings. This is what I would prefer to leave this at if I have not done the very difficult calculations to see how my CTs perform and see where I need to do this. These are very conservative settings, and unless I have company standards that dictate me to change those, or I have done those other calculations, I would recommend slope 2, 95%. That's the default. I'd probably change that to around 85%. I can add a pickup delay. I don't want to do this in this example because there's no need in doing this. I've got decent CTs here, and I've got decent settings, and those should prevent me from misoperating for a through fault. So I'm not going to add any intentional delay. The next thing I really need to do is to set my inhibit mode, right? Now, this is something that I don't like. All the inhibit functions are set pretty good, except the inhibit mode. They're all set by default pretty good, except the inhibit mode, right? The two choices here are second harmonic block or disabled. You want second harmonic block. 20% is a decent value there. That's what the electromechanical relays were stuck at. But on inhibit mode, I suggest that change to average. You could do it 1 out of 3 or 2 out of 3, but I think average is a much better setting. Okay. Now, if I wanted to operate additional relays, I can choose those additional output relays. If I wanted to operate additional outputs on this 845, I could choose those relays to operate here. No, there we go. Okay, so I'm operating relay 2. There's also an instantaneous differential function. Now, the instantaneous differential function is by default disabled. It is a differential that operates unrestrained. So whenever the differential gets above that quantity, it operates, even if it's second harmonic content. I am not a big fan of an unrestrained differential. So I prefer to leave that disabled. It is not faster than the traditional element. Okay, then the next two settings that we really want to have is anything that trips the relay. Anything that trips the relay needs to be in the time tag sequence of events record. And by default, this particular element is in the events. You know, our other option is to disable that, which means it would not be in the time tag sequence of events. That'd be a bad idea, especially since I have tripped it. I am tripping from this element. So since I'm tripping from this element, I'm going to leave events enabled. I'm going to set that to enabled. And then targets. Targets are the targets that appear on the front of the relay. So there is an HMI on the front that will produce a target when this element is operated. There's also LEDs, trip LEDs, that when this element trips, those LEDs will illuminate. So the choices here are either latched, self-reset, or disabled. For something that trips, this needs to be latched. And so what that means is when the relay trips, that trip LED and the 87L or the 87T transformer differential operand on the HMI will stay asserted, and you can see that until you hit the reset button on the front of the relay, or you reset the targets on the relay. That is what this should be set at. It should be set to latched. The other choices are either disabled, which means you get no indication that it's tripped, the other choice other than disable means you get nothing And then self-reset means that as long as the trip is, you targets, you get the alarms on the front of the HMI and the LED. When the trip clears after the breaker opens, this goes away if we set it to self-reset. So we want to set this to latched and latch that in so that it stays latched in. So that is our settings for the percent differential. Now, also at a minimum, we probably want to have a phase time overcurrent. So let's set a phase time overcurrent as well. So let's set this phase time overcurrent. Let's set this first one to provide some backup protection there. So we want to set that one to tripped. We get to choose an input signal. So our J1, if we go back to that screen, J1 is the H winding. So since J1 is the H winding, we're going to leave this as a high side overcurrent, right? And we're going to have to use ETAP or something like that, ETAP or Easy Power, to actually come up with our settings so that they coordinate with the downstream devices, coordinate with the transformer inrush, and coordinate with the transformer damage curve. But let's say we've done that work and we get our settings and we choose 8. So 8 is the pickup in this particular example, 8 times CT. And we can choose a particular curve here. Right now we're using IEEE moderately inverse. And remember, the pickup moves the curve from right to left and the time dial moves it up to down. And so that gets that set. Now, the input mode here that we can choose from is either phaser or RMS. And the difference between the two is a little nuanced, right? So RMS is not the peak of the waveform divided by the square root of 2. It is actually the energy under the waveform. So RMS would include harmonic content, right? Whereas the phaser is going to filter out any harmonics. So the phaser is a better protection for faults, because if we have a fault, all of the fault current is going to be at the fundamental. Now, if we're in an environment with a whole lot of harmonic content, a whole lot of noise, and we want to model this time overcurrent as a transformer overload, and we're worried about that harmonic content overloading the transformer, we could change that to an RMS quantity. Let's leave it as phaser right now, and we'll leave it as a backup overcurrent. So again, I can set this as a directional element. I'm going to leave this disabled. So that means it will be a non-directional element. Anytime the current gets over that 8 times CT, it will pick up regardless of the direction. I could set this, if this were at a generating station, I might be interested in setting a voltage restrained overcurrent, because my voltage might collapse to a large degree when I strike a fault. That's especially important at generating stations or other places where my voltage might collapse to the point that I don't have enough current. I'm going to leave that disabled at the moment. And again, if we go down here to events, I want to make sure that my events are enabled so that it's in the time tag sequence of events record. And instead of being self-reset, since I'm tripping from it right up here, I want to change that to latched, and then I'm going to save that. And that pretty much gets my time overcurrent and my slope differential characteristic, as well as my transformer differential for this particular model transformer in this 845 relay. So with that said, I think I've got 15 minutes left to address any questions that Mike wanted to leave for me.
Actually, I think that we have a very shy group today, Terry. Only a couple of questions.
They probably have all left because of my internet problems. Again, let me apologize, guys. I don't control the weather, as you know. We're having some electrical storms in East Tennessee right now, and every time I heard it thunder, the next noise I heard in my headset was the little beeping sound telling me that I had lost connectivity. So I am sorry about that, guys. Sorry for that loss of connectivity. Happened 2 or 3 times during the event, and I know that was frustrating. It was frustrating for you as well as me. So my apologies again for that.
Hey Terry, there's a couple of questions that I answered, so maybe you can build on it a bit. So one of the questions is about connecting the CTs with electromechanical relays and to be able to correct for phase shift and magnitude compensation, which cannot be done in electromechanical relays like in the microprocessor relays.
That's right. Okay. Let me get my presentation back down here and we'll find that slide. Yeah, that seems to be another issue where I cut out, right? So back in the day when we just had electromechanical relays, what we had over here on the right was how we would do this, right? Excuse me, I'm having trouble between my right and my left. What we have over here on the left is how we would do this, right? So what we would do is we'd take these the Y winding CTs, we'd wire those in delta, right? We'd wire those in delta, and we'd take the Y winding CT, the delta winding CTs, and we'd wire those in Y, right? So this CT, it'd be connected here, and there'd be a restraint coil here, right? And then this CT, these delta CTs over here, they'd be connected here, and there'd be a restraint coil here, right? Now, connected to those 2 restraint coils would then be an operate coil here, right? Now, what you'd see on the secondary of these CTs then, I've lost my cursor again. Hold on a second. There it is. So what we'd see on the secondary of these CTs is this delta connected winding would have a 30-degree phase shift. So this secondary would have the 30-degree phase shift from what we would expect right here. But these CTs here, you know, even though they're on the Y winding, they're connected to delta. So because of that, they've got a 30-degree phase shift as well. So what that means is this delta connected winding took care of the phase shift across the transformer also. Got that 30 degrees back. So what that sort of look like is, let's say you're passing current in that direction, right? So this looked like, let's say this is the Y winding is the H. I'm sorry, I drew it from the bottom. If you're used to drawing it from the top, let's draw it from the top. Okay. So let's say current's flowing in that direction, right? So let's say this is the H winding on the top, the X winding on the bottom. So the H, let's say the H is at 0 degrees, right? But the X is at minus 30, sitting right down here. Okay. So what we would see, so this is the H and this is the X, right? So there's the H and there's the X. What we would see coming into the relay, so I'm going to draw a little H and a little X as the secondary of the CTs. So these guys are in Y, so little H is sitting right here still at 0 degrees, right? Now, little X though he is in Delta. He's also wired sort of backwards here. So he's sitting here, right? Because of 180-degree phase shift. But then because we've wired that in Delta, little x, pretend that's a little x and that's a big X. Little x is sitting here at minus 0 degrees. Now, let's make this fun too. Let's say this side is 138 kV, right? That's 138 kV, and this side is 13.8 kV, right? So then let's make these CTs, these Y-connected CTs. We'll make those, I don't know, what do you think? Let's make those 300 to 5s. 300 to 5s. And let's make these Delta connected VTs on the 13.8 kV winded. We'll make those 3,000 to 5, right? All right. So what then happens is if we've got, so what we sort of are doing here is we're matching up the CTs as best we can. And in this case, because I chose this 13.8 to 300 or to 138 kV transformer, I've chosen it's exactly 10. So it's easy to choose my CTs and match them up as best I can. So for example, if I've got 150 amps flowing into the H winding, I got 1,500 amps flowing out the X winding. On the secondary of those YCTs, if I got 150 amps flowing into the primary of the transformer, flowing out of those secondary of those CTs is 2.5 amps, right? So that's 2.5 amps, 2.5 amps, 2.5 amps at 0 degrees, right? Now, flowing out over here, since I got 1,500 amps flowing out on that side, that looks like 2.5 amps at 180 degrees. So 2.5 at 180 degrees, right? Those vectorially sum to 0. And that vectorial summation is happening right there at that dot. See that dot right there? Now, in reality, that's not going to be 0 because those CTs aren't perfect. That's going to be some small quantity. So this coil here, this that I'm going to label R, it's a restraint coil, and there's a restraint coil here. Both of those restraint coils are providing opening torque. So they're going to provide restraining torque to keep the contacts apart. And then the operate coil is sitting right here. And it is the current flowing through it is providing restraint torque. Or excuse me, it's providing operate torque to close the output contacts. So as long as the restraint, the current in the restraint is a large enough percentage of the operate torque, it stays open. And so that's how this was accomplished in electromechanical relays. It's a little bit complicated also because there was a filter circuit sitting out here, right? And that filter circuit was tuned to the second harmonic, and that filter circuit also provided restraint torque and for the transformer inrush when you first energize the transformer. Okay. Are there any other questions?
What's a good book for protective relay recommendation?
Okay, there's a lot of good ones. One of them that you can still get out in the public domain from different places. I don't know if John Levine is on this presentation, but I know that it's on his website, is the Art and Science of Protective Relaying. So that is a book that was written by GE way back in the day, and it's a great book that covers the art and science of protective relaying, practical practices and principles. The book that I most typically use or reference, everyone just calls Blackburn. And the reason they call it Blackburn is because it was written by Lewis Blackburn. He was a Westinghouse guy, but nonetheless, he wrote a great book. And his book is titled Protective Relaying Principles and Applications. That's another good resource. That's the one that I most often reference. Unfortunately, Blackburn, you can get that on Amazon, whereas the Art and Science of Protective Relaying, it's in the public domain. You can get that for free. You can find that as a PDF.
Yeah, that's available in the Grid Solutions website.
Okay.
As well as the application, the protection and application guide, which is a modern version of the Arts and Science of Relays. It has some comms stuff in it there. That's also available on the Grid Solutions website.
Yep. Another thing that you could do too is, if you're looking beyond books, is you could just do a Google search. I could give you the HTML, but I don't think that's important. It's great. It's helpful right now. If you just do a Google search of GE Grid Solutions resources, you're going to get to our resources page. And our resources page is filled with videos of different, some of them are videos like the talk that I've given today, except without the internet interruptions and the drops. These are professionally done things. But there's a lot of videos there. Some of those videos are expert talks, and they're talking about applications like we're talking about today, transformer relays. Some of those videos are how-to videos. They're like, how to connect to an 8 series relay. The expert talks are something like we had today. They're targeted around an hour. Those how-to videos are a lot more digestible. They're usually targeted at 10 minutes or less. But that's another great resource. So that's the grid.
I think we lost Terry again.
Yeah, we only have a couple of minutes, Eduardo. There's no other questions that I see. So if you want to add anything, and we can close it up.
No, I don't see any other questions, Mike. So yes, we're on the hour. Thank you, Terry, for an excellent presentation, regardless of all the technical difficulties today. But I would also want to thank Mike Ramalashan, Christine Kreitz, and Paul Smith, which were the application engineers supporting Terry today, answering your questions. And please feel free to reach out to us in the next coming days if you have any questions regarding this topic or anything else related to protection and control. We are here to help you with any issue at your facility, design or operational. And be on the lookout for the next invite. We're planning to have our next webinar on Thursday, August 13th. The invitation will go out Monday, Tuesday of next week. I've had a few of you asking me where the link is. We'll send it as part of the invitation. And once again, thank you so much for taking the time to participate in today's webinar. Hopefully it was productive and educative to you, and we look to see you next time. With that said, I think we're ending the session.